This is the 13th video in a series devoted to introductory proof writing. And mostly today we're going to talk about how to disprove statements. But before we look at that, I'd like to look at a chart of mathematical statements, be they true, false, or unknown. So generally, if a mathematical statement is true, we call it a theorem or a proposition or a lemma, but I'll just put this all under the larger heading of theorem. So in other words, these are true mathematical statements. If we have a false mathematical statement, well, we just call that a false statement. I'm not sure there's a really decided upon word for that. But something whose truth is unknown is generally called a conjecture. So we have things that are true, things whose truth or falsehood is unknown, and things that are definitely false. So let's look at some examples of things from each of these categories. So the Pythagorean theorem is something which we know is true. So of course we know that says that the sum of the squares of the lengths of the legs of a right triangle equals the square of the length of the hypotenuse. And so this theorem was discovered lots of different places independently, which is kind of interesting. Then also Fermat's last theorem is known to be true. So that's fairly recently in the grand scheme of things. It's also known that there are infinitely many primes. In fact, we proved that in a previous video. Some things that are known to be false are this statement right here. So there exist natural numbers a, b, and c such that a cubed plus b cubed equals c cubed. So that would contradict the truth of Fermat's last theorem. Another statement which we know to be false is that all continuous functions are differentiable somewhere. And this is maybe not known to students taking a class like this, but once you take an analysis class, you'll learn about a function that is continuous everywhere but nowhere differentiable. So it's one of these crazy analysis examples. And then what about some conjectures, some things that we don't know if they're true or false? Well, we don't know if all perfect numbers are even or not. So the existence of an odd perfect number is not known. Also, we don't know something called Goldbach's conjecture, which says any even number bigger than or equal to 4 is the sum of two primes. So we don't know if that's true or not. Also, we don't know if there are infinitely many primes of the form n factorial minus 1. These are unknown. Okay, so now that we've got these three categories like described, let's talk about what a mathematician does. So mathematicians are generally interested in taking things from this category, so the category of conjectures, their truth is not known, and transporting them into the category of theorems or to the category of false statements. So we've been working on proving things. We'll talk about how to disprove things a little bit today. Then there's another really important thing that mathematicians do, and that is come up with conjectures in the first place. And so they go out here to the ether of mathematical results that are just floating around waiting to be discovered, and then they find one and put it in this category of conjectures. And then it either sits there if it's really hard, or if it's not really hard, it probably gets proven immediately to be a theorem or a false statement. Now I'd like to tell you a little bit of a story about this process of going to the ether to find a conjecture. And in fact, I had a professor in grad school who did analytic number theory. So this is number theory that's on the edge of analysis. And she talked about going down to Princeton on the weekends, so this was in upstate New York, to visit with a professor. And she told a story that there would be a very large line of junior faculty from all over the region outside this senior professor's door, just asking for conjectures to work on. So I guess when it comes down to it, this ether might just be the outside of some professor's door who's more senior than you are. Okay, so now back to how to disprove statements. So let's just say, in short, how do you disprove a statement P? Well, you show that the negation of that statement is true. So to show that P is false, you would show that not P is true. But just to have some very simple outlines down on the board, what if we've got a universal statement? Let's say we want to disprove the universal statement for all x in S, P of x. Then you would want to show that its negation is true. But what that boils down to is finding an x in S such that not P of x. So that for all statement turned into an existential statement. Then if we'd like to disprove this conditional statement, P implies Q, you would find some x, I'm missing an x here, such that P of x is true and Q of x is false. So that's the negation of the conditional. What about disproving an existential statement? Well, that's going to turn into a universal statement. So to disprove there exists x in S such that P of x, you would show for all x in S, not P of x. Okay, so let's get down to some examples. So now let's look at our first two examples of things to disprove. So we'll show that these are false. The first one is that for every natural number n, f of n equals n squared minus n plus 11 is prime. Now let's say we were not told that this was false. So if we were not told that this was false, we would guess that it's false because there's no like simple closed formula for a prime. So there's no polynomial expression that always outputs a prime. That's kind of a well-known fact. So we know that this must not always be prime by that well-known fact. But now what we need to do is find a particular n so that when we plug that value of n in there, we get something that's most definitely composite. But it's not so hard to find one. In this case, 11 works. So let's note that f of 11 equals 11 squared minus 11 plus 11, but that's equal to 11 squared, which is not prime. So this was a for all statement that we disproved by finding a particular x, that x was equal to 11. Now let's look at another for all statement that we'll disprove, and that is for all sets A, B, and C, we have A set minus B intersect C equals A set minus B intersect A set minus C. So this one's maybe a little bit trickier to get some intuition behind, but this is false as well. And we'll show that it's false by making a particular example where this fails. So let's maybe look at the following sets. Let's take A to be the set containing 1, 2, 3. We'll take B to be the set containing 1, 2. And we'll take C to be the set containing 2, 3. Great. And now let's look at either side of this would-be equation, this would-be identity. So let's start with the left-hand side. So we have A set minus B intersect C. Okay, but that's going to be the set containing 1, 2, 3, set minus the intersection of B and C. But what's the intersection of B and C? It's exactly this number 2. Great. So just to be very clear here, this B intersect C became this singleton 2. But now if we do that set difference, we'll get the set 1, 3. So here we get 1, 3. Okay, good. So that would be the left-hand side. Now let's look at the right-hand side. So let's do A set minus B intersect A set minus C. So that'll be 1, 2, 3, set minus 1, 2, and then intersected with 1, 2, 3, set minus 2, 3. Okay, good. But now let's do that simplification. So if we take 1, 2 away from 1, 2, 3, we're just left with the singleton 3. So this turns into the singleton 3, and then we need to intersect that with what's left over after doing that set difference. But that's pretty clearly the singleton 1. But then if we intersect the singleton 3 and the singleton 1, we get the empty set. So let's see what we have. We have the empty set from one direction and this doubleton 1, 3 from this other direction. These are clearly not equal to each other, which means we found an example where this fails, but that disproves this statement. Okay, let's do another. So for our next example, we'll look at the following statement. So we will disprove this. So this statement is false. And the statement says there is a real number x such that x to the fourth is less than x, which is less than x squared. So let's maybe get started on this, and we'll disprove this by negating the statement and show that the negated statement is true. So let's say that this orange arrow means to negate our statement. But perhaps to do that carefully, we should maybe write this into symbolic logic. So notice that in symbolic logic, this says there exists an x in R such that x to the fourth is less than x and x is less than x squared. So what I did is I took this compound inequality and turned it into an and statement. I think that's the best way in order to negate this kind of thing. Okay, so now negating it, what happens is the existential turns into a universal. So that'll turn into a for all x in R. And then we negate this and statement into an or statement while negating each of the sub-statements, if you will. So we'll have x to the fourth is bigger than or equal to x, or x is bigger than or equal to x squared. Okay, so now let's write that in words. So for all x in R, x to the fourth is bigger than or equal to x, or x is bigger than or equal to x squared. So that's what we will indeed show. And we'll break this into a couple of cases. And these cases are maybe inspired by how we know the real numbers act from maybe a pre-calculus or a calculus class. So for my first case, I'll look at everything where x is less than or equal to 0. So in other words, x will come from the interval minus infinity up to 0, including 0. Okay, but if x is negative and we take the fourth power of x, then x is positive. But a positive number is always bigger than or equal to a non-negative number, so that actually takes it all the way home. I don't think much needs to be said about that. So we have x is less than or equal to 0 is less than or equal to x to the fourth. Again, because every even power of a real number is bigger than or equal to 0. But then pulling out the middle there, we get this part of our or statement. So I think we're good to go there. Okay, so now let's look at our second case. So for case number 2, we'll take the case when x is between 0 and 1, but not including 0 and also not including 1. But then from there, I think we can just take the well-known behavior of the real numbers, that if you take a number between 0 and 1, not including 0 and not including 1, and you square it, you get something smaller. So for instance, if your number was 1/2 and you squared it, you would get 1/4. That's smaller. If your number was 2/3 and you squared it, you would get 4/9, which is smaller. So I think this immediately leads you to see that x squared is strictly less than x as needed. Now this may seem a little bit like a cheat, but I think it's okay in our process. And in fact, for one of the upcoming cases, we'll do it a little bit more carefully. But that being said, I think this is okay for here. Okay, so now let's look at case number 3. Case number 3 is maybe the most boring case, which is x is equal to 1. But if x is equal to 1, we have x squared equals x to the fourth. But equality satisfies, well, really both of those. Okay, so now let's move on to case 4. And so case 4 will be x is bigger than 1. So it's on the interval from 1 to infinity. So if it's on the interval from 1 to infinity, then that means we can write x as 1 plus a, where a is on the interval from 0 to infinity. So I think that's pretty clear. And then from here, we're going to look at the fourth power, because if x is larger than 1, we expect it to satisfy this inequality here. So let's look at x to the fourth, which is equal to 1 plus a to the fourth. And then multiplying that out will give us 1 plus 4a plus 6a squared plus 4a cubed plus a to the fourth. And that's by binomial expansion, which we learned about in a previous video. But now let's notice that everything that I'm underlining in orange is strictly bigger than 0. So since all of that is strictly bigger than 0, I can drop it and I've made something smaller. So that means this object is bigger than 1 plus 4a. And then again, since a is bigger than 0, I can replace that 4a with an a, and I've created something smaller. So this is strictly bigger than 1 plus a, but that's equal to x. So now reading from here to here, we see that we have achieved this inequality right here, or a strict version of this inequality. Okay, so let's see. Have we covered all real numbers? We have. So we covered non-positive numbers here, everything on the open intervals from 0 to 1 here, everything equal to 1 here, and everything on the open interval from 1 to infinity here. So that covers all real numbers. And in each of those cases, we either satisfied this inequality or this inequality. So that means we've proved the negation of our starting statement, which means our starting statement was false. We're going to end the video by looking at a little bit of a conjecture, one that we can actually prove. So this conjecture says there are distinct x, y, z, which are integers, such that x to the y is the same thing as y to the z. And in order to approach our decision of whether or not this is true, we would really just play with some integers. I think that's the best way to go about this. But since this is an existential statement, all we have to do is find distinct integers satisfying this rule. So after playing around with it a little bit, we'd come up probably with the following example. And I actually think this is the only example, although you would have to check that. So let's notice that 2 to the 16 is the same thing as 2 to the 4 times 4, which is the same thing as 2 to the 4 raised to the 4 power. But 2 to the 4 is 16. That's 16 to the 4 power. So let's notice here we have 16 in the exponent. Here we have 16 in the base, which means we've done it. We have x equals 2, y equals 16, and z equals 4 is a solution. And that's all we need to do to prove that this is true. Okay, now I'm going to leave you with some warm-ups. So for the warm-up exercises, your goal is to decide if they are true and then prove them if they are true or prove that they are false by appropriate methods. So this first one is f of n equals n squared plus n plus 41 is prime for all natural numbers n. So decide if that is true or false and then prove it accordingly. Next is if n is an integer and n cubed minus 3n squared is even, then n is even. And finally, if x and y are real numbers such that x cubed plus 4x is less than y cubed plus 4y, then x is less than y. So I guess I'll give you a hint here that 2 of these are false and 1 of these is true. And that's a good place to stop.